I'd like to start by asking a question I often ask my classes at MIT. How many of you are happy this morning? Raise your hands if you're happy. And how many of you are not happy this morning? Okay. And how many of you haven't raised your hand yet? Well, this is a very happy audience, and I'm very happy to be here with you today. What I'd like to do today is talk about collective intelligence, what it is in the first place, how to measure it, and perhaps most importantly, how to improve it. So first, it's important to realize that intelligence is not just something that happens inside. Intelligence also arises with groups of individuals. In fact, I define collective intelligence as groups of individuals acting collectively in ways that seem intelligent. Now, by this definition, collective intelligence has existed for a very long time. Armies, countries, companies, families, examples of groups of people working together in ways that at least sometimes seem intelligent. But in the last few years, we've seen some very new kinds of collective intelligence enabled by the internet. Think of Google, for instance, where millions of people all over the world create web pages, link those web pages to each other, and then all that knowledge is harvested by the Google algorithms so that when you type a question in the Google search bar, the answers you get often seem amazingly intelligent, at least for a certain sense of the word intelligent. Or think of Wikipedia, where thousands of people all over the world have collectively created a very large and amazingly high quality intellectual product with almost no centralized control, and by the way, in most cases, without even being paid. So I think these early examples, like Wikipedia and Google, early examples of internet-enabled collective intelligence, I think they're not the end of the story. I think they're just barely the beginning of the story. I think we're going to see many, many more examples of internet-enabled collective intelligence over the coming decades. And if we want to try to predict what's going to happen, and especially if we want to try to shape or take advantage of what's going to happen, I think we need to understand those possibilities at a much deeper level than we do so far. So that's our goal at the MIT Center for Collective Intelligence, and also, in a sense, my goal for us this morning. Now, one way of framing a core question here, a way we use a lot at the MIT Center for Collective Intelligence, is this. How can people and computers be connected so that collectively they act more intelligently than any person, group, or computer has ever done before? If we take that question seriously, I think the answers will look very different from the organizations we mostly know today. And I'd like to take that question seriously. I'd like to talk today about some of the kinds of research we've been doing to help answer this question. I'd like to talk about 4 projects, primarily the first one, but a little bit about the other 3 as well. If collective intelligence is important, as I certainly think it is, then it would certainly be nice to be able to measure it more precisely. So the first project I'd like to tell you about is one we've done to try to measure collective intelligence using the same statistical techniques that are used to measure the intelligence of individuals on things like IQ tests. We're applying those tests here, not to measuring the intelligence of individuals, but to measuring the intelligence. Intelligence mean, and the work I'll be telling you about here is from an article in Science magazine a few years ago. My co-authors are listed here on the slide. Now, what does intelligence mean in the sense that psychologists use the word when they measure it on intelligence tests? You might think that different people are good at different things, and that if you're good at, say, math, you're not very good at reading, or if you're good at reading, you're not very good at math, and different people have different dimensions of intelligence. It turns out, empirically, that that's not really true. That people who are good at one mental task are, on average, good at lots of other mental tasks. It seems counterintuitive to some people, but this is in fact one of the most widely replicated and in some ways most surprising results in all of psychology. This result was first documented scientifically by Spearman back about 100 years ago, and he called this general cognitive ability that predicts people's performance on many different kinds of cognitive tasks. He called that ability G, for general cognitive ability. And it is, in fact, this G that intelligence tests measure. In fact, if you give a whole bunch of people a whole bunch of mental tasks, whether that's separate individual things to do or looking at grades in courses, etc., and you do a factor analysis of all those people's performance on all those different tasks, then you will find a first factor that explains typically 30 to 50% of all the variance on all the tasks, and way more, usually more than twice as much of the variance as the second and all the other factors. So that's the psychometric statistical definition of intelligence at the individual level. The very fact that that exists, I think, is pretty interesting scientifically, but it's not only of academic interest. It turns out that this is of practical importance in a number of ways. Because this factor, this intelligence factor that you can measure for individuals, you can measure that in less than an hour. In fact, you can get a pretty good approximation of it in only a few minutes with simple paper and pencil tests. And that factor that you can measure so quickly and relatively easily turns out to be significantly predictive of a lot of things that matter to us in the real world. It, for instance, predicts people's performance in school, their grades in classes. It predicts their performance in many occupations. It even, it turns out, is predictive of life expectancy. People with higher IQ, on average, live longer. So all that is interesting, I think. The question that we began to wonder about, though, is whether there even exists a similar factor for groups, like there does for individuals. As far as we can tell, no one had even asked that question before. And so we asked it. And in order to answer it, we brought a bunch of different groups of people into our laboratory. We recruited these groups from the general public in the Boston and Pittsburgh areas using things like Craigslist. We had groups of 2 to 5 people each, almost 200 groups, about 700 people altogether. And we had each group work on a number of different tasks together. I'll tell you a little more about the tasks in a moment. We also had each individual do a few other tests, like intelligence tests, on their own as well. In order to be sure we had a wide and relatively representative sample of tasks for the groups to do, we used a taxonomy of group tasks developed by someone named McGrath, who has 4 different categories of group tasks. For instance, one of them is the category of generating things. There we used a task of brainstorming uses for a brick. So people are generating ideas about how to use a brick. Another kind of task we had was some actual intelligence test items. So we had people performing something called Raven's matrices tasks as a group, not just as individuals. We had them planning a shopping trip subject to a whole bunch of constraints on where things were and how perishable things were and so forth. And we also had groups typing segments of a long text passage into a shared document like Google Docs. So those are the different tasks we had people do. We had all these groups do all these different tasks. And then we did a factor analysis, essentially, to see whether the same thing would happen with groups as happens with individuals. It turns out the answer is yes. There is a single statistical factor for a group, just as there is for an individual, that predicts how well the group will perform on a wide range of very different tasks. This diagram shows what's called a scree plot. It shows the percentage of variance explained by the different factors in a factor analysis. And as you can see, the first factor explains a significant amount, 30 to 50% roughly, of the variance, much more than any of the other factors. It doesn't mean that there aren't other things that matter, but it means that this single factor is surprisingly predictive of performance on lots of different tasks. Mathematically speaking, this factor, which is what we call collective intelligence, is a linear combination of the group scores on all the different tasks they performed, with the weights of the different scores being calculated to maximize the predictiveness across all the tasks. If C exists, that is interesting to begin with, but then the next question is, what does C, which is the term we used in homage to Spearman's little g, we use little c for collective intelligence. If there is such a collective intelligence factor for a group, what does it predict? Well, one thing it predicts is the performance of the groups on other tasks not used to calculate C in the first place, other more complicated tasks that involve lots of different skills. We did 2 studies and had 2 different criterion tasks in this sense. In one study, the groups were playing checkers against a computer checkers program. In the other study, they were building structures out of Lego blocks, fulfilling a whole bunch of different rules about what the structures could do and so forth. It turned out that the group's score on the collective intelligence tasks was significantly predictive of their performance on both of those criterion tasks. And interestingly, the average and maximum intelligence of the individuals in the groups were not predictive of the group's performance on these tasks. Now that's particularly interesting, I think, because we also, in a separate side study, had individuals alone performing these tasks, and their performance was correlated with their individual intelligence. So when somebody did these tasks alone, smarter people did better. But when groups of people did these tasks as a group, their average and maximum individual intelligence was not even statistically predictive of performance. Their collective intelligence, however, was. So that's what C predicts. The other kind of question to ask is, what predicts C? In other words, what factors can allow you to predict how collectively intelligent a group will be? So the thing we worried about before we did this work was whether this would be a kind of trivial thing. That is, there might be such a thing as collective intelligence, but it would just be the average of the individual intelligence of the people in the group. So it turns out that the average and the maximum individual intelligence of the group members is correlated with the group's collective intelligence. But that correlation is only moderate. The results are shown here. So what that means intuitively is that just having a bunch of smart people in a group doesn't necessarily make a smart group. I suspect many of you knew that already. You've probably experienced that, as I have. Just because you've got a bunch of smart people doesn't mean the group itself works very intelligently. But here's a very precise scientific demonstration of that. So if it's not just having smart people in the group that makes the group smart, what else is it? Well, we looked at a bunch of different factors that we thought might affect that or might predict that, including things like how psychologically safe people felt, how motivated they were, etc. Most of those things that we thought would have affected it didn't. But we did find 3 factors that were significantly correlated with the group's collective intelligence. The first was the average social perceptiveness or social intelligence of group members. Now, the way we measured this was by showing people pictures of other people's eyes and asking them to guess what emotion the person in the picture was feeling. When you have a bunch of people in a group who are good at doing that, then the group, on average, is more collectively intelligent than when you don't. The second thing that was significantly correlated with the group's collective intelligence was the degree to which people talked about the same amount. In other words, if 1 or 2 people dominated the group conversation, then on average the group was less intelligent than when people participated more evenly.
Hear, hear.
Yes, I see some heads nodding around the room about that one. The third factor we found that was significantly correlated with the group's collective intelligence was the proportion of women in the groups. More women was correlated with more intelligent groups. I usually get a big reaction when I give that result.
You have more women.
So a few of you are... So it turns out, by the way, that last result is mostly mediated by the first one. In other words, it was known before our work that on average women score higher on this measure of social perceptiveness than men. So one possible interpretation of our results is that what you need for a group to be intelligent is to have more people in the group who are socially perceptive or socially intelligent. And then it may not matter whether those people are men or women, as long as they have that ability. But if you know nothing about a person besides their gender, you'd be more likely to get that with women than with men. I personally kind of like that explanation. But we don't know for sure what's going on. Some people, for instance, have speculated that maybe men act differently when there are women in the group. That may be part of the effect. We don't know for sure. Now, one other thing people sometimes think is that this is a diversity result. A lot of people would say that having women in the group would help make the group do better in all kinds of ways. But actually, this is not a standard diversity result. The standard diversity argument would be that groups are better when you've got a mix of different kinds of people in them, and probably they would say that the best groups would be the ones with about equal numbers of men and women. We didn't design our study to specifically look at this question, but to the degree we have data about this, it suggests that this effect may be roughly linear. In other words, it may be better to have more women in the group, possibly even up to all or almost all women. Here's the detailed graph of our results by proportion of women. The point that has all women is not the highest point, but the point that has half and half women, the one right here in the middle, is one of the lowest points. So there's at least some indication that this is not a straight diversity result, that it may be better to have more women, perhaps all the way up to all women. So I guess we don't stop for questions along the way. Okay?
That was a lower correlation. The higher correlation is 41 of equal turn taking. How is that related to women and this intelligence?
Well, when we put all three of these factors into a regression at once, the one that remains as significant is this one, the social perceptiveness.
So it takes over the variance that is accounted for by equal distribution at 40.
Yes, so
how does that, how did it wrap into it? You have 26 is the correlation for social perceptiveness independently, and then when you put it in a multiple regression, it swallowed the rest, even bigger ones?
Beats me, but strange. That's how it happens statistically. Yes?
What factors did you check if they predict C but they didn't predict C?
I probably can't remember all of them off the top of my head, but one was the sense of psychological safety in the group. You ask people, how safe do you feel? Another one was essentially how much do you like these people? Like, would you like to spend time with them outside of work or outside of the group? We also looked at personality. So we gave them the standard 5-factor personality test, introversion, amiability or agreeability, et cetera, compliance. None of the individual factors were predictive. In other words, the average of the group's scores on each of those factors was not predictive of their collective intelligence. There were several more, but those are examples of the kind of things we looked at. One other thing related to this importance of social perceptiveness is another study we've done, not yet published, since the study that I described to you so far, where we had two different conditions. We had one set of groups working together face-to-face, like the ones we've talked about so far. The other set of groups, the other condition, were groups who worked together online. They only communicated via text typing and filling in the answers in an online administration of the tasks. So we found similar results in both the face-to-face and online groups. In fact, most surprisingly, we found that the measure of social perceptiveness was equally predictive of the group's collective intelligence in both cases. In other words, even when people couldn't see each other's eyes at all, they couldn't see each other's faces. There were a whole bunch of people in a big room. They didn't know who was in their team and who wasn't. Even when they couldn't see each other's eyes at all, their ability to read emotion in people's eyes was predictive of their group collective intelligence. Now, what we think that means is that the measure of social perceptiveness that we used must be actually correlated with a much broader set of interpersonal skills. Not only does it mean you're good at reading emotions in eyes, but you're probably good at reading between the lines of things people type and imagining what they're thinking based on other clues and so forth. So to us, that is even more support for the importance of this kind of social intelligence or interpersonal skill in helping to create intelligent groups. Question?
Yeah, since you're taking questions in this presentation, is it a myth that there is an inverse relationship between intelligence and social capacity? Like the myth of the hyper-intelligent person unable to interact with anybody, that would explain that if you get many intelligent people in a group, well, they're not social people.
Yeah, it's an interesting question. Now that you asked the question, I don't think we actually looked at that in our data, but my guess would be that it is a myth. In other words, that these things are uncorrelated. My guess would be that they are uncorrelated, not negatively correlated. But it's an interesting question. Okay. Anything else before we go on? Okay. So what does this mean? I think one question is, or where can we go with this? One question is, what we expect but don't yet know is that this measure of collective intelligence, which you can administer in less than an hour, we can get a pretty good version of it in 15 minutes, it looks like. We suspect that this would predict the performance of a group on lots of other tasks that would take much longer, just as happens with individuals. And one of the things we'd like to try is measuring that. Measuring, for instance, whether a group's score on this collective intelligence test, if it were a sales group, would it predict how well they're able to sell over the coming year? Could you predict how successful a software development team would be on a bunch of different projects by giving them a little test like this? Could you predict how successful a top management team or a board of directors would be by giving them a test like this and predicting how well they'd perform, or how well they'd respond to a wide range of different challenges? We suspect that would be the case. Now, another thing that I think is perhaps even more interesting is that with individual intelligence, you can measure it and you can predict with those measurements, but it's very hard to change the intelligence of an individual, certainly when they're older than 5 or 6 years old. With groups, it seems eminently possible to increase the intelligence of a group. At the minimum, you could take out some people and put in other people. That could certainly affect it. But we suspect there may be a number of other ways to increase the intelligence of a group. For instance, increasing the number of people in a group. Making it bigger may make it smarter, at least up to some level. Or changing the norms people have for interaction or the incentives they have for working together. Or providing the right kinds of online support tools may help make a group more intelligent. One of the most intriguing things, for instance, is if you think about face-to-face groups, generally people would say the optimal size for a face-to-face group is somewhere between 5 and 10 people. It seems possible that with the right kinds of computer collaboration tools, it might be possible to have groups that get more and more intelligent, not just between 5 and 10, but you might be able to have groups of 50 or 500 or even 5,000 that are more intelligent than any smaller groups. So you may be able to get much, much more intelligent groups with the right kind of collaboration support tools. So that's the first project on measuring intelligence. Let me just talk briefly about 3 other projects. One is combining human and machine intelligence. This is a project I did with Iftak Nagar, referenced there. The 2 hypotheses we were exploring in this were, first, that the combination of people and computers together would be better than either one alone at making certain kinds of predictions, and that prediction markets could be an effective way of making that combination. So what are prediction markets? You know what prediction markets are. How many do not know? Okay, most of you. Okay, in a prediction market, people buy and sell predictions about possible future events. So, for instance, if you were trying to predict who will be the next winner of the US presidential election, and you thought it was going to be Hillary Clinton, you could buy a prediction, a share predicting that event. And if you were right when the election was over, that share would be worth $1. If you were wrong, the share would be worth 0. So if you think about it, what you should do is buy a prediction only if it is cheaper than your probability assessment for the event. So if you think there's a 60% chance that the event will happen, that Hillary Clinton will be elected, then you should be willing to buy a share of that prediction for anything less than 60 cents. And you should be willing to sell it to someone for anything more than 60 cents. So in that sense, the prediction market is a way of assessing and actually averaging people's probability assessments of these future events. And the prices in this prediction market, the prices at which people buy and sell these prediction shares, are essentially probability estimates for the events that may occur in the future. It turns out that prediction markets have been used for a number of things in the past, and they're often surprisingly accurate at making these predictions. For instance, they've been used to predict US presidential elections for over 20 years and are usually more accurate than the polls. They're used to predict product sales and a number of other things. So to test the combination hypothesis, we picked an example of a task that was intended to be analogous to things like predicting what competitors will do in business or what an enemy will do in war, or what a terrorist might do. But we picked a more sanitized example, which was predicting what will be the next play in an American football game, whether the next play will be a run or a pass. And we had humans watch videos of a football game, stop the video before each play, and ask them to participate in a prediction market of whether the next play would be a run or a pass. We also had computer algorithms, very simple machine learning algorithms trained on one previous game that made the same prediction and participated in the same kind of prediction market based on 3 pieces of information: what down it was, how many yards to the next down, and whether the last play was a run or a pass. So in some conditions, we had humans in prediction markets only with other humans. In other cases, we had computers only with other computers. And in some cases, we had humans and computers both participating in the same prediction market, buying and selling things with each other. What we found, I did 20 different sessions, 15 and 19 people each, etc. What we found was that the combination of people and computers, as we had hoped, was more accurate than either one alone. We also, if you think about it, you might wonder whether one might be more accurate than the other just by taking more risks. So we used a measure of risk-reward finance theory. It's called the Sharpe ratio. It's basically what's your expected value divided by how risky you're being. So it turned out that on that measure, the combination of people and computers was much better than either one alone. That is, it took less risk and was still more accurate. Both of the measures require you to put some cost on inaccuracy. So you have to figure out how much to charge or to penalize predictions when they are inaccurate. There's another way of assessing how much information is included in a group or a person's predictions called a receiver operating characteristic curve, where basically you want to have as much information as possible regardless of how risky you choose to be with your predictions. Here, the further up and to the left a curve is, the better it is. And here, too, the combination of people and computers is better than either people alone or computers alone. Yes?
I understand how a person decides whether a player is going to pass or a computer does it. How did you combine that?
So the combination was they just both participated in the same prediction market. So if the person thinks it's likely to be a run, they would be willing to buy a prediction saying run for a relatively high price. If they think it's not going to be a run, they'd sell any they had and not buy anymore. And we also had the computer algorithms that were programmed to make an assessment of probability, and then they had some other rules as to how much they would buy or sell based on the difference between the current price in the market and their assessment.
You average price between the two predictions.
We didn't actually average them. We actually let them both participate in the same market. So if a person said, I'm willing to sell this for X, and a computer program thought, I'm willing to buy that for X, then the transaction would occur in the market.
So you actually kick in both transactions and then take the profit or the loss based on the actual result.
We let both kinds of actors participate in the same prediction market. We had an actual market going on in the software. People could look at a screen and decide whether they wanted to buy another share or not. And the agents were also deciding whether to buy or sell shares at those prices.
I ask because I'm from a markets background. I'm just trying to figure out, so is it a profit and loss model? So you average whether, so I say he's going to run, the computer says he's going to pass. I'm wrong, computer's right. He makes a certain amount of money, I lose a certain amount
Correct.
of money. So the net difference is the result for the combined.
No, the thing we look at is the price, the average price, actually the closing price. And we take that as a prediction, a probability prediction. So if the closing price is 0.6, we treat that as a probability of 0.6. And then if the actual answer was they did run, that would be a 1. So the 0.6 prediction was off by 0.4, and you'd penalize the prediction by 0.4. It turns out that in addition to having those probability estimates, which we use to gauge the accuracy, each of the individual participants in the market would end up with a certain amount of money. If they were accurate in their trading, they would make money. If they're inaccurate, they would lose money. Okay? Okay, so I'll assume that we've taken some of the question period already, and I'll spend a few more minutes finishing up. The result here is that that the combination of people and computers can be both more accurate and more robust to different kinds of errors than either one alone, and that prediction markets do in fact appear to be a reasonable way of making that combination. The thing I'd like to talk just briefly about is work we've done on what we call mapping the genomes of collective intelligence. My co-authors here are listed on this slide. We looked at a bunch of different examples of what were interesting cases of collective intelligence, Wikipedia, Google, etc. And we tried to look for the design patterns, the common patterns that came up over and over in those examples. We called those design patterns genes, by analogy to biological genes. And we identified a set of about 19 of those patterns that came up over and over in these different cases. The most important of them are shown here. Here's an example which I won't go through about how they all fit together. If you analyze the community of people that developed the Linux open source software system, it embodies all of the genes shown here. Loosely speaking, the community of people creates new software modules using what we call the crowd gene, because anyone who wants to in a large group can participate. You don't get assigned to do it, you self-select to do it. They do that for motivations of love and glory, and they do it in a way that is interdependent among themselves, so that's what we call the collaboration gene. The community also depends on someone making decisions about which of the modules people create are going to be included in the next version of the system. That's not done by the crowd, it's done by Linus Torvalds and his lieutenants, again for love and glory, through what we call the hierarchy gene. So for each of these different genes, we've identified different examples and different conditions under which they're useful. For instance, one gene, contest gene, here are some examples of it. Here are some conditions under which it's useful. In the long run, we think it's possible to identify a wide range of different design patterns that can be used to help create organizations and other kinds of systems that are collectively intelligent in new ways that take advantage of new technologies.
How did you identify the genes?
We did that inductively. So we looked at a bunch of examples and we said what's common here and how do we define that and so forth.
Okay, so no statistical analysis or anything.
We actually in the early days tried doing some statistical analysis, but it turned out to be more useful, we thought, just to do it kind of intuitively and inductively.
And how reliable was the classification of the examples to the genes? So the intuitors figure out what the genes are and then somebody else classifies according to that.
We could have tried to do that systematically. We didn't actually do a systematic test of that, but we think that we were relatively successful at defining things in an unambiguous way. But it's an interesting question. It would be interesting to do that more systematically.
It's not out of skepticism, but what was the measure of success? Because if people interpret something and they're happy with the interpretation, is that success?
In this case, that would be a sort of intuitive measure of success. That is, does it make sense to people? Does it give them insights? Does it help them think about how to do things in the future?
Because the other variables are what is the test-retest reliability and what is the predictivity?
Correct. Correct. In this case, we were aiming for a more intuitive and pragmatic value rather than a purely statistical value. So as you can probably tell, I'm giving you a wide range of different studies where we've been addressing different kinds of audiences using different methodologies. And in fact, the last study I want to talk about very briefly is yet again a very different approach. It's a large-scale field study, if you want to call it that, but it's more like action research where we're actually intervening not just studying what other people are doing. The project here is called the Climate CoLab, a number of collaborators, many of which are listed there. Here we're thinking about the problem of what to do about global climate change. Many people would say this is one of the most important problems facing our species today. Most people would also say it's a very difficult, complicated problem. It's affected by all of our actions. It particularly affects all of us. And many people would say that the largely top-down approaches we've been using to address this problem so far haven't really worked very well. Those are all reasons for pessimism. But I think there's at least one reason for optimism, which is that we now know from examples like Wikipedia and Google that there are now ways of harnessing the collective intelligence of people all over the world at a scale and with a degree of collaboration that was never possible before. So our goal in this project is to apply this crowdsourcing approach to the problem of figuring out what to do about global climate change. To do that, we've created an online platform called the Climate CoLab, and a community of people using that platform, also called the Climate CoLab community. The community includes some of the world's leading experts on the science and policies related to climate change. But it also includes a worldwide group of people, over 13,000 people as of a couple of days ago, including students, technologists, NGO members, professors, business people, people from all walks of life and literally all over the world, who are together developing and analyzing proposals for what to do about global climate change. The proposals can include any ideas they want to include about technological changes, economic, political, educational, anything they want. In order to keep the proposals grounded in the actual physical and economic realities we face, the proposals at the global level need to also include some quantitative assumptions about things like the emission reductions that would result from those changes. And then there are built-in computer simulation models that predicts the consequences of those actions for things like temperature change, sea level rise, and so forth. We've used a set of contests, annual contests, to organize most of the activities of this group. For several years, the winners presented their ideas in briefings at the United Nations in New York and the US Congress in Washington. Last year and again this year, they present their ideas in a conference held at MIT. Here's some of the statistics about the number of users, the number of expert judges and advisors involved, and so forth. Now, in the first couple of years, we had people work on the whole problem of what to do about climate change. But we came to believe that it was much more useful to break the problem down into more focused subproblems. So in the last few years, we've done that with focused subproblems on things like how can you generate electricity with fewer emissions? What can city governments do about rising sea level? How can we change social attitudes about climate change? And then once you've broken the problem down into pieces, you need some way of putting the pieces back together. So starting this year for the first time, we have had our first integrated contest, where people put together proposals that combine other proposals and look at the cumulative effect of all these other ideas. So the kind of research questions here are, how can you do large-scale collective problem solving? How can you attract and motivate people? How you can divide problems and put the pieces back together? We think those are a big set of collective intelligence problems, which we're investigating here in the context of one particularly important and difficult problem about climate change. So the final questions would be things like, how can we measure collective intelligence? How can we design new forms of it using new technologies? And in general, how can we create more intelligent organizations? Now, I'd like to close with one more bit of eye candy and some very grandiose thinking. I think as our world becomes more and more closely connected with many kinds of electronic communication, it will become increasingly useful to view all the people and computers on our planet as part of a single global brain. And perhaps our future as a species will depend on how well we're able to use our global collective intelligence to make choices that are not just smart, but also wise. Thank you all very much.